maybe we can sneak our way back from string theory into black holes.
Yeah, yeah.
What was the idea that you and Kamran developed with the holographic principle in string theory? What were you able to discover through string theory about black holes, or that connects us back to the reality of black holes?
Yeah. So that is a very interesting story. I was interested in black holes before I was interested in string theory. I was
Sure.
sort of a reluctant string theorist in the beginning. I thought I had to learn it because people were talking about it. But once I studied it, I grew to love it. First, I did it in a sort of dutiful way. These people say they've claimed quantum gravity. I ought to read their papers at least. And then the more I read them, the more interested I got, and I began to see, they phrased it in a very clumsy way. The description of string theory was very clumsy and
Mathematically clumsy, or just the
mathematically
interpretation?
clumsy.
Okay, got
Yeah,
it.
it was all correct, but mathematically clumsy. But it often happens that in all kinds of branches of physics that people start working on it really hard and they sort of dream about it and live it and breathe it, and they begin to see interrelationships, and they see a beauty that is really there. They're not deceived. They're really seeing something that exists. But if you just kind of look at it, you can't grasp it all in the beginning. And so our understanding of string theory uh, in 1985 was almost all about you know weakly coupled waves of strings colliding and so on. We didn't know how to describe a big thing like a black hole in string theory. Of course, we could show that strings in theory in some limit reproduced Einstein's theory of general relativity and corrected it, but we couldn't do any better with black holes than before my work with Kuhlmann. We couldn't do any better than Einstein and Schwarzschild had done. Now, one of the puzzles, if you look at the Hawking's headstone and also Boltzmann's headstone, and you put them together, you get a formula for, and they are really central equations in 20th century physics. I don't think there are many equations that made it to headstones. and and they're really central equations, and you put them together and you get a formula for the number of gigabytes in a black hole. Now, in Schwarzschild's description, the black hole is literally a hole in space, and there's no place to store the gigabytes. And it's not too hard to, and this really was Wheeler and Bekenstein and Hawking, to come to the conclusion that if there isn't a sense in which a black hole can store some large number of gigabytes, that quantum mechanics and gravity can't be consistent.
We got to go there a little bit. So how is it possible when we say gigabytes that there's some information? So black holes can store information. How is this thing that sucks up all light and is supposed to basically be super homogeneous and boring? How is that actually able to store information? Where does it store information? On the inside, on the surface?
Yeah,
Where's
yeah.
and what's information? I'm liking this ask 5 questions to see which one you actually answer.
Oh, okay.
I'm
So
gonna
when you
ask you a
say
bunch.
that, I shouldn't try to memorize them and answer each one in order, just answer
No,
them
I don't
now.
know. I don't know what I'm doing. I'm
Okay.
desperately trying to figure it out as we
Okay.
go along here.
So Einstein's black hole, the Schwarzschild black hole, they can't store information. Stuff goes in there and it just keeps flying and it goes in the singularity and it's gone. However, Einstein's theory is not exact. It has corrections. And string theory tells you what those corrections are. And so you should be able to find some alternate way of describing the black hole that enables you to understand where the gigabytes are stored. So what Hawking and Bekenstein really did was they showed that physics is inconsistent unless a black hole can store a number of gigabytes proportional to its area divided by 4 times Newton's constant times Planck's constant.